Hello. In this video, we'll be discussing some of the physics behind why two common moves in ice skating work, namely the glide and the shrimp spin, or the shrimp shortened. The clips we will be using are from the 2005 Disney movie Ice Princess. Now, since this is the most popular Disney movie in existence, no copyright infringement is intended by this video. The first ice skating move we'll analyze is the glide. I'll play it for you as it appears in the movie. As you can see, the ice skater is moving in a relatively linear direction, keeping her body pretty straight. She then leans to her right and finds herself moving in the direction of an arc. What are the physics going on here? Since this is Pete's physics classroom, we will start our investigation by identifying a lens. We will look at this move through the lens of angular momentum. When the skater is skating in a straight line, if we think of the skater's skates as a fixed point, then the mass of the skater is centered with the fixed point, and she has no impact parameter. On the other hand, when the skater leans, then she is not centered with her skates, which is again our fixed point. This means that she has an impact parameter, or R in the displayed diagram. Similar to the bullet and block problem presented in the Veritasium videos, this means that the skater has angular momentum due to her leaning and increasing her impact parameter, or R as depicted in the diagram again. If we take the direction of the skater's velocity as positive, this means there is an increase in angular momentum from before the skater leans to when she is leaning. Since this lean does not happen instantaneously, there is a change in time to consider, which is also positive. Therefore, the skater leaning creates a positive torque in the system, which is why she begins to move in a circular direction. Mind you, we could have selected a rotational dynamics lens for this problem, as the skater leaning means she has changed her moment of inertia, which thus will change the torque in the system. However, we chose angular momentum instead, due to the impulse created when the skater shifts her weight, and also to avoid some gross calculations involving the moment of inertia. Right, now that we know what we're talking about, let's start throwing some numbers around. We guessed that the skater's height is about 68 inches tall, and about 30 of those inches belong to her torso and upwards. The rest is all in her legs, or the remaining 38 inches. This distinction is important. From looking at the video, we saw that the skater leans her upper body a little bit more than the rest of her body, so we need to account for this in our model of the skater's leaning. We guessed that the skater leans in around 15 degrees and leans her upper body inwards by about 5 more degrees than this, so 20 degrees total for her upper body. If we create two triangles with these two diagonal lines, then we can find the skater's impact parameter through some trigonometry. Here's another picture of the diagram. The internal angle of each triangle is 90 degrees minus the respective angle at which the skater is leaning, yielding 75 degrees for the lower triangle, or the leaning of her legs, and 70 degrees for the upper triangle, or the leaning of her upper body. We determined that the skater's impact parameter is approximately 20.096 inches by finding the impact parameter of her upper body and of her lower body and adding these together. Now, we guessed that the skater has a mass of about 90 pounds, which is roughly 40.1 kilograms. And we guessed that the skater's linear velocity is about 3 meters per second, again in the positive direction. As such, we can determine her angular momentum at the moment she finishes leaning. It comes out to about 61.353 kilogram meters squared per second. Since we know that torque can be expressed as the rate of change of angular momentum over time, we can find the torque that acts on the skater due to the change in angular momentum by determining the change in time. We guessed the period of time it took for the skater to lean was about half a second, meaning that the skater has a torque of about 122.706 Newton meters. This is consistent with the skater's observed motion. There is a torque acting on her, as we have just shown, and thus she gains angular acceleration and begins to move in a circle.
So you just saw the shrimp spin from Ice Princess, and you are now looking at some information about and calculations based off of her height to find her spinning radius, and we used a cylinder in order to find her moment of inertia, which we will show later. Okay, so here is how we found her height of her jump as well as the overall energy that it took to make the jump. But before any of that, I'm going to go ahead and explain how we found her weight and her speed or velocity in order to calculate the energy that is necessary as she goes into the jump. Okay, so in the video, she moves from the topmost neutral zone face-off spot to about the center of the rink. That's gonna be half of the entire neutral zone, which comes out to be approximately 7 meters or so, and it takes her about 2 to 3 seconds to do that. So we approximated that her speed's about 3 meters per second. So we found that the average 5'5" female during this time weighed about between 90 and 110 pounds. However, due to the fact that she's a figure skater as well as the fact that she is a child, we estimated that she would be approximately 80 pounds or 36 kilograms. Now that we have all the numbers, let's just get to the physics. So, there is very little friction between the ice and her ice skates themselves, meaning that any heat lost to friction is negligible. So we figured that kinetic energy would be converted into potential energy at the height of her jump and then would transfer back down into kinetic energy at the end of her jump. Using this, we could find kinetic energy initial using her mass and her initial velocity, as shown here, and then set that equal to potential energy, mgh, to find the height of her jump, which we found to be approximately 0.5 meters. Last and finally for this project, we found her angular velocity. We did this in two different ways. First, we took her overall revolutions, 12 revolutions, divided it by the 4 seconds that it took her to complete those revolutions, to find that her angular velocity should be approximately 18.8 radians per second on average. Next, because momentum is always conserved, and because she started with a linear momentum, we set that equal to her angular initial momentum, which, as momentum is going to serve, is going to be equal to the final angular momentum. So after some slight calculations, we found that the initial momentum would be equal to 108 kilogram meters per second. We set that equal to I omega, which, as shown here, we found I to be 1/2 36 kilograms times 0.56 meters, and that's because she's not using her whole leg as the radius. She's spinning approximately 1/3 down her leg, which came out to be approximately a 0.56 radius. So we use that as the radius squared, and we found that her angular velocity should be approximately 19.1 radians per second, which is pretty close to the guesstimate originally. Anyways, that's our projects. Thank you, and I'll see you in class.